Alright, this is 11.5, infinite geometric series. Objective, students will be able to find the sum of an infinite geometric series and write repeating decimals as fractions. So an infinite geometric series, this is a geometric series that has no end. For example, a bouncing basketball, right? Like, so if we had this basketball and it fell and it bounced, the next time it would bounce a little bit less than the first time, and so on and so on and so on. And in theory, this basketball keeps bouncing on and on forever, except for the fact that there's other forces at play here. And those bounces begin to become so small that it's apparently not moving at all. So here's an example of a infinite geometric series. 1/2 plus half of that, which is 1/4, plus half of that, which is 1/8, plus half of that, 1/16, and so on. Now we can calculate the sum of just these first four terms by just adding them together, right? This is called a partial sum. Partial sum. All right, well, but let's talk about this. What happens to r to the nth power as n approaches infinity? Remember r, what is our r in this situation? Looks like we're multiplying by 1/2 every single time. So if r is 1/2, question is, what happens to r to the nth power as n approaches infinity? Or we could say it as, what happens to r to the power of infinity? Well, we don't really know that. We can't just plug that in our calculator and figure it out, but we could take a look and see what happens as it approaches that. So for example, since our r is 1/2, what's 1/2 to the 10th power? And then what's 1/2 to the 100th power? And what's 1/2 to the 1000th power? We can keep doing this. Well, I do not have a calculator in front of me at the moment, but if you were to do this in a calculator, what you'd see is that eventually this number ends up being so tiny. It's going to end up being, a 0 followed by, 30 zeros or something like that. So it gets really, really close to 0. So we could say as r to the infinity, that's going to approach 0. Okay. Or actually, we could say r to the infinity actually equals 0. As n approaches infinity, this is going to get closer and closer to 0. So r to the infinity, if we actually could raise it to the infinite power, it would equal 0. Well, then let's take a look at our equation. If r to the n ends up equaling 0 when we get to infinity, then that would leave us with a sub 1 times 1 minus 0 over 1 minus r. And 1 minus 0 is just 1, and 1 times anything is just itself, so then we would have the sum of infinite terms equals the first term over 1 minus r. Well, awesome. This only works, though, when our r value is between -1 and 1. So we say when r is between -1 and 1, this will always happen, and so we say that the geometric series converges. The way I remember that is conform means, everybody's the same, and so eventually we're going to get to this same number, the sum. We're going to converge to a single sum. And is therefore called a convergent series. If it doesn't converge, we actually call it a divergent series. And we'll talk about that later. Okay, so the sum of infinite geometric terms is that equation we have right above. It's the first term divided by 1 minus r. It's a really simple equation. All right, well, let's put this into use with the same series we've been talking about. So here we have 1/2 plus 1/4 plus 1/8, and we have a visual of it, right? So here's a half of a square plus a fourth of a square plus an eighth of a square plus a 16th plus 30, and so on and so on and so on. Okay, and you can kind of visualize what this is going to add up to as we start adding smaller and smaller parts. Well, let's just see. I mean, it looks like it's going to add up to just one whole block, right? If this is a half of a block, then this is a whole block. Well, let's see. If a sub 1 is 1/2, and the r value is also 1/2 because we're adding half of it every single time, then the sum of infinite terms is going to be the first term, 1/2, divided by 1 minus the r, which is also 1/2. Well, 1 minus 1/2 is a half. So what's a half divided by a half? Well, it's the same thing as 1/2 times its reciprocal, 2 over 1. And you can see right away what's going to happen. 1 times 2 is 2, and 2 over 2 is 1. And so the sum is 1. Just like we had predicted from the visual, it would be 1 whole block. Okay, let's go on to the next page. So this first question here just says, does the infinite geometric series diverge or converge? Remember, let's do this. Converge means that the r is between 1 and -1, while diverge means that the r is either greater than 1 or that the r is less than -1. It's not in between those two numbers. And diverge means it's going to go on forever. So we have to first just identify what the r value is. So what's the r value of this thing? Well, it looks like I'm just multiplying by -1/3. Yeah, 1 times -1/3 is -1/3. So let's put a little negative there. This is -1/3. That is between 1 and -1. Therefore, this converges. All right, there will be a sum from this pattern. However, let's see the next one. It's written in sigma notation, so it might seem a little confusing, but the r value is just right here. The r value is 2. Well, 2 is not less than 1 and not less or not greater than -1. Well, it is greater than -1, so I guess that doesn't really work. But it's not less than 1. So we would say that 2 is greater than 1 and therefore it diverges. We cannot find a sum. It's just going to keep adding up to infinity. Okay, so what if they give us a problem like this in sigma notation, right? So let's look and see, what are they really asking here? They're saying, hey, we want the sum of the first term all the way to the infinite term, with the first value being 24, the r is -1/5. And this is a geometric sequence, or series, because this is 24 times your r, a sub 1 times r to n minus 1. That's this geometric series or sequence formula. So if we want the sum of that to infinity, then we just need the sum equation, which is a sub 1, which I'll do in blue, over 1 minus r, which I'll do in red. The reason for that is this is our a sub 1 value, and this is our r value. Okay, so let's just plug everything in. My a sub 1 is 24. And to do that in blue, over 1 minus my r value, which is -1/5. Okay, well, let's simplify this a little bit. 1 minus 1/5. That's actually the same thing as 5/5 plus 1/5, right? Because we know this becomes a plus, and we could rewrite that as 24 over 5/5 plus 1/5. So that's like 24 divided by 6/5. And again, we're dividing by a fraction, so we can just flip and multiply. So that's 24 times 5, 6. Right away, I see a 24 on top and a 6 on bottom. I know I can take something out of both of those. I can take a 6 out of both of those. Leaves me with a 4 and just a 1. And so I get 4 times 5, which is 20. And so the sum of all these numbers starting at 24 all the way to infinity, multiplying it by -1/5 every single time, is going to add up to 20. Simple as that. Okay, this last thing here, this is how to write 0.39 repeating as a fraction. And I kind of wrote it incorrectly here. Technically, we should write it as 0.39, and that repeating bar should only be over the 39. Well, what does this mean? Let's do the first method. This means that this is really 0.39, 39, 39, 39, and so on and so on and so on. And so we could think of this as 0.39 plus 0.0039 plus 0.000039, and so on and so on and so on. And so then we could write this as a fraction as 39 over 100 plus 39, and I added 2 zeros, so I got to add 2 zeros to my denominator, 10,000 plus 39. Add another 2 zeros and I get 1,000,000. And so on and so on and so on. Well, what is my R value then, okay? Like I have my A sub 1 value. My A sub 1 is 39/100ths. But my R value is actually 1 over, it seems to be 100, right? If you look at this, 39 times 1 is 39, and 100 times 100 is 10,000. So my R value is 1/100th. So I could actually find the sum of this, written as a fraction, using the sum of infinite terms formula, which is A sub 1 over 1 minus R. And I can plug that in. My A sub 1 is 39/100ths over 1 minus my R, which is 1/100th. And I would say that that's the same thing as 39/100ths. Sorry, I again meant to make this red. That's 39/100ths over, well, 1 minus 1/100th, that's 99/100ths. Well, and I could just again flip and multiply. 39 over 100 times 100 over 99. Hopefully you see these hundreds cancel out and we're left with 39 over 99. Now this can be reduced. We could take a 3 out of each of those. We take a 3 out of that, we get 13 out of 33. And so we just wrote 0.39 repeating as a fraction. There we go. There is another way to do it. It's a little bit simpler. So I think you guys will probably prefer this other method. So let's do that one. Starts off by just writing it as an equation. And typically we use S for the sum equals 0.393939, repeating, and so on and so on. And the idea is, well, what happens if we were to multiply both sides of this by 100? Well, we'd get 100s, and over here we'd get 39.393939, dot, dot, dot. And what happens if we took this first equation and we subtracted it from this new equation that we have? Oops, this would be a 0. Right, our first equation was 0.39393939. Well, 100s minus s is 99s. And 39.393939 minus 0.3939 is just 39. Divide both sides by 99. And look at that. We have the same fraction we started with on the last one. Again, it can be reduced down to 13/33. All right. And that's how you can write a repeating decimal as a fraction. Now, you may see a pattern here. A lot of these are just taking the number and putting it over 99 and then reducing. That'll probably be an easy way to do it for a lot of you. But I would recommend that you practice the math because that's the more important part of this. All right, I'll see you guys on the next video.